Hello, Professor Sargent here with you again for another Math 101 flipped classroom lesson. A system of equations is a collection of equations for which we are trying to find a point that is a solution to all of the equations in that collection. So sometimes they also get referred to as simultaneous equations. You want something that's simultaneously at the same time is a solution to all of the equations. Now, usually we're looking for just one, at least at this stage of the game, but there could be none at all. There could also be several, up to infinitely many solutions. We're going to restrict our attention right now to systems of linear equations. For example, we have two linear equations right here. And furthermore, in this section, we're going to restrict ourselves to viewing two linear equations with two variables and talking about how do we recognize whether something is a solution to one of those systems, talk about graphical and algebraic ways to solve systems of linear equations. When there are two variables and two equations, I refer to that as a 2x2 linear system. In the section after this, we'll take a look at 3x3 linear systems. And in section 3.3, we're going to look at some applications, although we may discuss during class time some ways of getting an idea why we would even bother studying this stuff in the first place. All right. So what's next? In this question, we are asked whether or not these two different ordered pairs are the solutions to the system. All this takes is arithmetic to check. And so what would that look like? Well, for the first ordered pair, put in 3 for x in the first equation and 0 for y. Do the arithmetic according to the order of operations. You get 6 plus 0 equals 6, which is what we wanted. But when we plug in 3 for x and 0 for y on the second one, that's equal to 3. That's not equal to 0. So if the ordered pair is not a solution to either equation, or even if it's a solution to one, but not a solution to the other, then it is not a solution to the system. It has to work in both. And so now I'll check out the ordered pair 2, 2. 2 times 2 is 4. 4 plus 2 is 6. So that point is a solution to the first equation. It's a point on the line. And then when we plug in 2 for x and 2 for y, 2 minus 2 equals 0. And that is what we wanted. So it's a solution to all of the equations that are in the system. It is a solution to the system. What's coming next is we're going to talk about, since I gave a hint there about this point being on the graph of the first line, and since it was also a solution to the second equation, it'll be a point on the graph of the second line, then we should expect that that's where those two lines meet. So we're going to talk about graphical solutions, and we'll also talk about one of two options for solving algebraically. That's coming next. We're going to take a look at the graphical approach to solving first, and we're actually going to use the same system that we just looked at. Pretend that we had not seen which was the solution, and we're going to look for that solution by graphing. We're going to find that by finding where two lines intersect. And then you could take the work we did just a few minutes ago as a check. Remember that to graph lines, we have seen three options. Finding two, better yet three, a third point as a checkpoint that are on the line, connecting to make sure that they are collinear, or by using the X and Y intercepts, or solving for Y to put these in the slope intercept form. I'm actually going to show you both of the last two. So first I'll put in 0 for Y in the first equation. 2x plus 0 is 2x. So solve 2x equals 6 by dividing both sides by 2. Get x equals 3. And that's giving us that 3 comma 0 is the x-intercept of that first line. Putting in 0 for x, 2 times 0 is 0, 0 plus y is 6. So y equals 6 when x equals 0. That's giving us the y-intercept of that first line, 0 comma 6. You could plot those 2 points and connect, perhaps do a third point as a checkpoint. But another option is to subtract 2x from both sides, and we get this version of the equation of the first line. That's telling us that 0, 6 is the y-intercept, just like we saw in the other approach, and that the slope is -2. I'm going to have to fix that in just a moment, -2. As for the second line, rather than doing intercepts, it's actually going to go through the origin. So I'd either have to plot 2 or 3 different points, or I could add y to both sides to get y equals x, and that's going to give us that the value of b is 0, telling us that 0 comma 0 is the y-intercept, and the slope is 1. All right, so fixing that, that was a -2. And in just a moment, we'll see the first line and then the second line plotted. We'll see if they intersect, and if so, where. If they do intersect, where they intersect is the solution to the system. All right, here we go. So first of all, I'm plotting the point 3 comma 0, the x-intercept of the first line, and then 0 comma 6, the y-intercept of the first line, connecting them. And notice how we have, if we had solved that for y instead, a y-intercept at 0 comma 6, and it is going down 2 and right 1. You can keep that going, down 2 and right 1, to get to that x-intercept. The second line we wrote as y equals x. So notice that that has a y-intercept of 0 comma 0, and it's going up by 1 and right 1 based on the slope. And then the point of intersection, luckily in this field of view, we can both see the point of intersection, and it's at a nice place at the point 2 comma 2. Which actually matches up with what we did in the first part of this. Now we're going to take a look at solving this by an algebraic method, substitution. The idea when solving a linear system of equations is to go, well in this case a 2x2 system, is to go from, if we're solving algebraically, is to go from having 2 equations with 2 variables down to 1 equation with 1 variable. Once you know the value of 1 variable, we can plug into one of the equations and solve for the other variable. So you don't have to do substitution twice to get the 2 variables. Do substitution once and then plug in to find out the other variable's value. Now, in this case, if you have a coefficient of 1 or -1 in front of one of the variables in one of the equations, it's going to make things even nicer However, I'm going to make this slightly more difficult just to make a point. So suppose we hadn't checked solutions at the beginning, or that we hadn't solved by graphing. Let's see what would happen when we solve this by substitution. I'm going to rewrite the first equation so that y is alone. We actually did that in the graphing, but I'll re-show the result of that. So we had rewritten the first equation as y equals negative 2x plus 6. Now that I have y alone in one of the variables, in one of the equations, I'm going to plug what we have here, that y is equal to, into the other equation. Be careful though, that y there is being subtracted. So we take all of that negative 2x plus 6 that y is equal to, that y was being subtracted in the second equation. So I'm going to subtract all of that. That means I'm going to have to distribute a negative sign. So when we've distributed the negative sign, it's going to change both of those signs there. I'm going to combine the like terms on the left-hand side. X plus 2x, that's 1x plus 2x equals 3x. And then I will add 6 to both sides. And that's going to give us that 3x equals 6. We can then divide both sides by 3 and find that x is equal to 2. Now that we know by doing substitution the value of one of the variables, I'm going to plug in 2 for x into one of the original equations there. Well, actually, I'll plug it in here in the rewrites and do some arithmetic. No more algebra. By the order of operations, I would multiply first and then add. I get that y is also equal to 2. Therefore, the point that is the solution is 2, 2. And again, we've already seen a check that 2, 2 is the solution to the system at the beginning. And now we're going to take a look at some special cases when we are dealing with 2x2 linear systems. We're going to look at these both by graphing and by substitution. So to graph the first line, since 2 and 3 both divide into 6 nicely, I'm going to find both the x and y intercepts. And we know what happens when we put in 0 for a variable. You multiply it, you get 0, you add, we get the other thing. And so the main thing is to show me that 2x equals 6, divide both sides by 2, and we get x equals 3. The thing to watch out for is if you have a minus or negative sign in front of one of those. Now to get the y-intercept, put in 0 for x. And we have 3y equals 6, so y equals 2. The y-intercept is at 0, 2. So I'm going to graph that line, plot the x-intercept at 3, 0, and the y-intercept at 0, 2, and then connect those. And next, we will take a look at graphing the second line. On that one, let's see here. We had y was not alone, but we do have 6y alone. So I could divide everything on both sides by 6. And that should say line 2. Fix that in a moment. But when we divide everything on both sides by 6, since dividing by 6 is the same as multiplying by 1/6, I have to distribute that to dividing negative 4x by 6 and 12 by 6. And that gives us that y equals negative 2/3 x plus 2. So we've got our y-intercept at 0, 2 and a slope of negative 2/3. All right, let's take a look at what that looks like. 0, 2, the y-intercept, and then go down 2 units and right 3 units, since the slope was negative 2/3, we're graphing the same line. Every point that is a solution to the first equation is also a point that is a solution to the second equation. That gives us infinitely many solutions. Let's see this by substitution now. Since we had already rewritten the second equation as y equals negative 2/3 x plus 2, I'm going to plug that in to the first equation. Remember, with substitution, when you substitute, you can't substitute back into the same equation. You have to substitute into the other equation. So, distribute 3 and combine like terms. The 2x minus 2x is going to cancel out, giving us 6 equals 6. You could even combine the like terms here and subtract 6 from both sides. You get 0 equals 0. Same number, when the variables drop out, same number means same line, and so infinitely many solutions. So what would happen if the variables dropped out and we had different numbers? We'll take a look at that in a moment, again, by both graphing and substitution. All right, we're going to take a look at our second and last special case, and we're going to look at it first by substitution. I'm going to make a claim about what this tells us about the number of solutions, and then check that by graphing, and that will wrap this up. Now, on this system, I don't have any positive or negative ones, so because the smallest number here with absolute value, negative 2, has the smallest absolute value of all of those coefficients, and it's nice to divide by 2 or negative 2. I'm going to rewrite the first equation by subtract 3y from both sides. You don't always have to solve for y when you are using substitution. Solving for y is a matter of getting slope-intercept. We don't always have to do that in substitution. So divide everything on both sides by negative 2. Negative 3 divided by negative 2. The negatives will cancel, but we don't get any reduction beyond that. And then positive 24 divided by negative 2 is negative 12. You take that, sorry, that's y. You take that rewrite of the first equation and plug it in for x in the second equation. Distribute that 4. In this case, you can think of 4 as 4 over 1 if you need to, but the 4 over 2 reduces. You're going to have 2 times 3y minus 48 minus 6y equals 12, and 2 times 3y is 6y. (6y) minus 6y, when you combine the like terms, you get these two different numbers, negative 48 equaling 12. If you went any further, you could add 48 to both sides and get 0 is not equal to 60. In this case, when all the variables dropped out and we get different numbers, I claim there is no solution. I started off with the assumption that there was a solution to the system of equations, which would have given me a nice number for x and a nice number for y. It didn't. I came up with this contradictory statement of 0 equaling 60. That's not true. So what that must go up against is my initial assumption that there was a single solution. Now, by the way, as I bring up the graph, there are only three possibilities when you have two lines. Either they are intersecting at a single point, or the two equations were really of the same line, or they could be parallel because they have the same slope but different y-intercept. I'm going to solve both of those for y so that I could get slope-intercept and graph those. All right, so on that first one, I add 2x to both sides, and then I divide everything on both sides by 3 so that I get y equals 2/3 x plus 8. That gives us a y-intercept for that first line at 0.8 and a slope of 2/3. With the second one, subtract 4x from both sides, and then divide everything by -6, everything on both sides, and that gives me that y equals 2/3 x minus 2. So the slope is the same, the slope is 2/3, but the second line has a y-intercept at 0, -2. We're seeing the first line graphed in blue here, and the second line graphed in red, and because they have the same slope but different y-intercepts, they are parallel. Therefore, there can be no solution. The solution would have to be where they cross, and that's not happening here. So again, have the variables drop out and you get the same number. You were really looking at the same line, just the equations were written two different ways, but it's the same line, and so there are infinitely many solutions. Whereas here, when you have the variables drop out and you get two unequal numbers, then the lines are parallel and you have no solutions. Hope this helps. I'll see you in class.